California promised a 220-mile-per-hour train that would shoot straight through earthquake country and beat the plane from San Francisco to Los Angeles. 17 years later, the state has spent well over $10 billion, torn up farms, demolished homes, and poured miles of concrete in the middle of nowhere. There is still not a single mile of operational high-speed track. This is not a story about a late train. It is a story about how you can design a project so ambitious that geology, politics, and money slowly crush it long before the first passenger sits down. In 2008, California voters were told they were buying a finished system for about $33 billion, with trains running by around 2020. The promise fit on a ballot card: electric trains at 220 miles per hour, San Francisco to Los Angeles in 2 hours 40 minutes, cheaper than flying, cleaner than driving, no new taxes needed beyond the initial bonds, because ticket revenue would help pay the bills. It sounded like a rare win in American infrastructure, a project that would prove the United States could still build at the same scale as Europe or Japan. On paper, the route looked simple. Trains would leave downtown San Francisco, cross the Bay Area, drop into the Central Valley, shoot down the long, flat spine between farm towns, then climb back through the mountains into Los Angeles and continue on to Anaheim. In reality, every section that touched mountains, cities, or fault zones turned into a separate mega project. Each one came with its own alliances, lawsuits, and enemies. In the early years, the easiest decisions were political. The hard ones were hidden inside rock layers no voter ever sees. The gap between the brochure and the ground began to open almost immediately. As engineers started mapping the real route in detail, cost estimates doubled, then climbed again. Tunnels that had been drawn as clean, straight lines on diagrams turned out to cross through fractured rock, high water pressure, and moving faults. Land that was assumed to be available turned out to be covered by farms, warehouses, and neighborhoods whose owners were willing to fight in court for years. Each mile of progress bought in lawsuits, design changes, and environmental reviews was a hint of what was coming once excavation began. Then came the choice that quietly doomed the original timeline. Instead of starting in the dense cities where passengers live, the project started in the middle of the Central Valley. Politicians could call it the backbone of the system. Engineers called it something else. It was the only place where they could actually build without immediately smashing into mountain tunnels or downtown property fights. The first physical proof that California high-speed rail existed was not a train, not a station, and not a tunnel. It was a series of concrete viaducts running over orchards and fields, far away from the coastal cities that had voted for the project. Diablo Range, through a corridor known as Pacheco Pass. That name on a map hides a very specific engineering problem. The only way to keep high-speed rail speeds through that terrain is to bore an extremely long tunnel under the hills, instead of weaving around them on the surface. This is not a short cut-and-cover culvert. It is a tunnel, counted in tens of miles, deep enough that rock pressure, heat, and water become permanent enemies. Inside a mountain like that, every meter of advance has to be bought. A tunnel boring machine the size of a small office building is lowered into a carefully excavated launch cavern. Its cutter head may be 30 feet or more in diameter and weigh hundreds of tons. In competent rock, it can eat through 50 or 60 feet a day. In crushed, waterlogged ground, that same machine might fight all day for 10 feet, or stop entirely until crews stabilize the face. Behind the cutter head, the machine is basically a mobile factory. Conveyor belts carry out broken rock. Hydraulic rams press precast concrete segments into place to build a permanent lining. Grout systems pump cement into gaps to stop water and prevent the mountain from squeezing the tunnel shut. Every system has to work at the same time, in a cramped tube where heat from motors and geology can push air temperature past what feels comfortable for a human body. All this effort is happening under a landscape cut by faults. A fault zone is not a single clean crack. It is often a wide band of shattered rock, full of weak layers and open paths for groundwater. When a tunnel hits a major fault, the rock can behave like wet sand instead of solid stone. The pressure of the mountain can push that material into the face of the machine like slow-motion lava. Engineers have to change tools, change support systems, and sometimes freeze the ground, or pump out water faster than it enters just to move forward. Each of those adaptations costs time and money that never fit neatly into early estimates. In the South, the route faces something even less forgiving. To reach Los Angeles, high-speed trains must cross the Tehachapi Mountains and the San Gabriel Mountains, and they must do it in a state built on the San Andreas Fault. A mountain tunnel in an ordinary region is a problem of rock strength and water pressure. A mountain tunnel in California adds the question of what happens when two tectonic plates decide to shift several feet in a few seconds. A tunnel lining has to survive not just constant load, but sudden horizontal offsets that can shear it apart. That is why any path across these mountains becomes a swarm of tunnels, bridges, fault crossings, and emergency cross passages. Each element must be designed not just for today's ground, but for the way the ground will try to move over the next 50 years. When you stack these realities together, the original price tag starts to look more like a polite guess than a serious budget. Long twin-bore tunnels, each with their own emergency escape tubes and service galleries. Fault crossing zones, where tracks have to be designed to be realigned after an earthquake. Ventilation caverns big enough to hold extraction fans that can clear smoke if a train catches fire underground. Access shafts wide enough for rescue vehicles to descend. None of that was visible in the early headlines. All of it is mandatory once the project commits to crossing the mountains at speed. See long concrete viaducts marching across fields, new overpasses lifting local roads over a future right-of-way, and sections of graded embankment that look like a straight scar running to the horizon. To a casual observer, it looks like a railway that is almost ready. To anyone who builds rail systems, it is the skeleton without any organs. Concrete guideway by itself does not move trains. High-speed rail needs heavy, continuously welded rails, anchored precisely to sleepers. It needs a hardened, ballastless track structure on viaducts, where loose stone would be thrown away by vibration. It needs electrification systems running above the trains, with masts, tensioned wires, and substations powerful enough to feed trains drawing megawatts. It needs signaling and train control systems capable of monitoring the position of every train to within seconds and enforcing safe braking distances automatically. It needs fenced right-of-way, intrusion detection, dispatch centers, maintenance depots, storage sidings, and stations built to handle thousands of passengers at peak, with platforms at exact heights. None of that is there yet. What exists is mostly earthworks and structures, the part of the project that is easiest to show in photographs when politicians need proof. Bridges are visually impressive. Graded embankments look like progress, but they do not generate a single ticket. 100 miles of finished concrete without electrification is just an elevated road that nothing can drive on. The Central Valley segment is effectively a very expensive promise that trains might one day use this corridor if the more difficult parts of the system are ever funded and built. This choice created a strange kind of risk. The least useful segment in terms of ridership is the one closest to completion. People do not dream of riding high-speed rail between farm towns. They imagine stepping onto a train in the heart of San Francisco and stepping off in the heart of Los Angeles, skipping airport security lines and freeway traffic. That dream is still blocked on both ends by mountains. The Central Valley concrete, no matter how well built, cannot fix that. Theoretical, the project's cost estimates climbed far beyond what voters were promised. A system once advertised in the tens of billions crept into the territory of 100 billion and beyond. That number is not just accounting trivia. It changes how every outsider views the project. At tens of billions, high-speed rail competes with other big-ticket items. At 100 billion and up, it competes with entire categories of public services. For that amount of money, a state can rebuild highways, modernize transit, harden critical buildings against earthquakes, or fund decades of education programs. Every new cost estimate forces a silent question. Is a faster train between two coastal cities worth giving up multiple other wins that might be less glamorous but more certain? Cost escalation also exposes the fragile logic of the original business case. Early models assumed high ridership, stable costs, and a world where construction inflation would behave. Real projects rarely get that lucky. When costs go up, but ridership projections do not move in lockstep. The cost per passenger climbs. That in turn draws more scrutiny. Analysts begin to test assumptions. How many people will really switch from flying if airfares stay competitive? How many drivers will abandon the interstate if they still need a car at the other end? How much are travelers willing to pay for a train ticket when low-cost airlines can adjust prices in real time to fill seats? As reviews multiplied, independent experts pointed out that the original ridership forecasts were optimistic at best. They relied on best-case behavior, not cautious assumptions. If actual ridership comes in at half of what was forecast, the picture changes completely. Instead of a train that pays its own operating costs, the state may be left with a system that needs ongoing subsidies just to cover electricity, maintenance, and staff. That is before paying back any of the capital cost. Eventually, the weight of these numbers reached the national level. Federal transportation officials looked at the rising budget, the lack of completed core segments, and the limited near-term benefit, and decided that continued support at previous levels was hard to justify. When a major funding partner steps back, it sends a signal that goes beyond the dollar amount. It tells every other stakeholder that the risk profile of the project has changed. Angry that a train is late. It is about watching a live experiment in how far a democratic, legally constrained, environmentally conscious society can push a mega project in hostile terrain before the system itself starts resisting. There are no spectacular tunnel collapses yet, no on-site disasters that kill dozens in a single event. The drama is slower, but in its own way, more unsettling. Engineers are caught between what physics allows and what budgets will tolerate. They know how to drive tunnels through bad rock. They know how to build bridges that ride out earthquakes. They know how to ventilate long tunnels safely, and how to design escape routes that give passengers a chance when something goes wrong underground. None of that is magic anymore. It is a matter of time, equipment, and money. What they cannot do is make geology kinder, or move mountains out of the way to match an optimistic map. Politicians are caught between short election cycles and long construction cycles. A tunnel that takes 10 years to bore will outlast multiple governors and legislatures. Each new administration has incentives to rebrand, redirect, or distance itself from decisions made by its predecessors. That leads to changes in scope, renegotiated contracts, and shifting timelines that inject uncertainty into planning. Contractors adjust their bids and risk premiums accordingly. The project becomes more expensive because it is politically fragile, and it becomes politically fragile because it is more expensive. Taxpayers end up watching an uncomfortable trade. They see money going into viaducts in regions they will never visit, while their own local roads, transit lines, and bridges age. They hear about a future where a bullet train will glide through the state at airline speeds. They see, year after year, no train. For some, it becomes a symbol of why they distrust big government projects. For others, it remains a symbol of what the country could do if it ever committed fully to modern infrastructure, instead of stopping halfway. Underneath all of this is the reality that other countries have built similar systems. Japan drilled through mountains and under the sea. Europe threaded high-speed lines through centuries-old cities and across borders. China built thousands of miles of track in a fraction of the time. Comparing California to those examples is part of the appeal and part of the sting. Viewers who follow engineering know that the problems are not unique. They are universal. What changes is how each society chooses to face them. California high-speed rail sits at that intersection. It is technically feasible, financially painful, politically contested, and geologically hostile. It is far enough along that abandoning it completely would mean writing off billions in sunk cost. It is far enough from completion that no one can honestly promise a date when you will be able to sit in a seat, feel the train accelerate past 150 miles per hour, and watch the Central Valley blur by on your way from one coast city to the other. For an adult viewer, that tension is the hook. This is not a tidy success story or a clean failure. It is a slow-motion negotiation between ambition and constraint, told in concrete, rebar, court filings, and revised budget tables. The real question is no longer, can California build a high-speed train? It is, how much pain is the state willing to absorb, and for how long, before either the mountains give way or the patience does?